In 1.5, we're going to learn how to solve and graph inequalities, as well as how to write and solve complex inequalities. An inequality provides us with a larger range of solutions. Instead of saying x equals a certain number, we could have x be greater than a value, or it could be less than, or greater than and equal to, or less than and equal to. A couple of important things to pick up from our image here is, first off, the symbols. Notice that whenever we have something that is or equal to, how we have an equal to symbol along with our inequality. Second thing to notice, if it's just greater or less than, we have these open circles. Whenever something's greater than or equal to, or less than or equal to, we're going to use closed circles in graphing. So those are just a couple of small details, but they're going to be important when it comes to graphing our inequalities. So first, let's try to write an inequality given a sentence. And this is going to be really similar to what we did in 1.3, except now we're including inequality symbols. Here we have 5 fewer than a number t is at least 12. Let's look for our keywords. First, we have fewer, which tells us we're going to be doing subtraction. And then we have this word at least, which means that 12 is the minimum number that we could have. Since 12 is the minimum, our solution is going to have to be greater than 12, but it could also be 12, so we're going to say greater than or equal to. Now we just need to put the numbers into the expression. Since it's 5 fewer than a number t, t comes first. So we're going to do t minus 5. We already said our symbol is greater than or equal to, and it's greater than or equal to 12. Next, the quotient of a number L and 3 is no more than 15. That keyword of quotient is telling us we're going to be doing division, and no more than tells us that we have a maximum. And if we have a maximum, our values have to be less than or equal to that value. Now, what do we have the quotient of? Well, we have the quotient of L and 3. So it's going to look like L divided by 3. Then we already know our inequality is less than or equal to, and it specifically is less than or equal to 15. When it comes to solving and graphing an inequality, we're going to do the same way we did it with equations yesterday, but there's one catch. We are always going to flip the inequality sign whenever we are dividing or multiplying by a negative. Remember, when it comes to solving equations, we're going to use order of operations in reverse. So we're taking PEMDAS and we're going backwards. Since we're starting with addition and subtraction, we're going to subtract 1 to both sides, which leaves us with negative 3 times 2x minus 5 is greater than or equal to 3. Then we're going to divide by this negative 3 out in front on both sides. And that's going to give us 2x minus 5. But since we divided by this negative here, we have to flip our inequality symbol. So now it's going to be less than or equal to, and it'll be less than or equal to negative 1. Now we can add 5 to both sides, and we'll get 2x is less than or equal to 4. Divide by 2, and x is less than or equal to positive 2. With this solution, we can now graph it. We know that we're going to be at positive 2, and since it can be 2, we're going to put an closed circle. Then it's less than, so we're going to shade everything to the left since all those values are smaller than 2. Our next example is really similar, except here we have a fraction we're going to have to get rid of, and we have x on both sides of our equation. Remember that if we want to cancel out a fraction, we need to multiply by its reciprocal. So we're going to multiply both sides by 2 over 1, which is really just 2. And that will cancel our fraction out. So we have x minus 6 is less than or equal to, now it's 6x plus 14 on that right-hand side. Go ahead and pause the video from here, solve for x, and graph your solution. Come back and check to see how you did. Depending on which way you solved, you may have your answer written as negative 4 is less than or equal to x, or you may have it written as x is greater than or equal to negative 4. Both are saying the same thing. In either way, we're going to have a closed circle, and the closed circle occurs at negative 4. Then we have to shade everything that comes above negative 4, since the open part of our inequality is facing the x, and that means greater than. Let's take a look at how we can write and use an inequality. The length of a rectangular yard is 30 meters. So let's start off by drawing what we have. We know we have some kind of a yard, it's in the shape of a rectangle, and the length portion is 30 meters. The perimeter is at most 90 meters. Here we have that keyword at most again. That tells us this is our maximum amount, and that means our inequality symbol is going to have to be less than or equal to. We want to describe the width of the yard, so that is our unknown. Let's start off by writing an equation that relates all of these together. Since we're dealing with perimeter is 2 times the length plus 2 times the width. Normally we would say equal to, but since we have an inequality, we need to go back to the problem to see which symbol we're using. That keyword at most tells us that the perimeter is less than or equal to 2 times the length plus 2 times the width. Now we can go and plug in what we know. We know that our perimeter, P, is 90, and we said the length is 30. So we're going to have 90 is less than or equal to 2 times our length, which is 30, plus 2 times the width. Now we just need to solve for the width. Now we have that 90 is less than or equal to 60 plus 2w. Subtract 60 on both sides. So 30 is less than or equal to 2w. We'll divide by 2, and that means 15 is less than or equal to w. Again, we have this written in kind of an odd notation because we're used to seeing the variable on the left-hand side. So we could flip this around. We can say the width is greater than or equal to 15. Notice how the big portion of our inequality symbol is facing towards the W, and when we flipped it around, it's still facing towards the W. So make sure when you flip the order of your inequality, you also flip the inequality symbol to match. In 1.4, we talked about how equations could be sometimes, always, or never true. The same thing works for inequalities. If an inequality is always true, then that means we're going to have a true statement. If it's sometimes true, then we would have x is greater than, or maybe it's less than, or equal to a given number. If it's never true, then we're going to have a not true statement. Now let's take a look to see what this looks like. In our first example, we're going to distribute this negative 2 to the parentheses. We're going to get negative 6x minus 2 is greater than negative 6x plus 7. We'll try to move our x's to the same side, so we're going to add 6x on the left to cancel it out, and we'll add 6x on the right. But it also cancels out here on the right, which means all we're left with is negative 2 is greater than positive 7. Now we need to ask ourselves, is this a true statement? Well, no, negative 2 is not greater than 7. Therefore, this is a never inequality. That means that there's no number we could ever plug in for x that's going to make this inequality be true. We're going to start out the next example the same way, starting by distributing that 5. So we'll have 10x minus 15 minus 7x is less than or equal to 3x plus 8. We're going to need to combine our like terms over here on the left. So 10x minus 7x gives us 3x. Then we have minus 15 is less than or equal to 3x plus 8. Go ahead and pause the video and finish this one off. Come back to see if you're right. Since our x terms cancel out and we're left with negative 15 is less than or equal to 8, and it's a true statement, this is an always inequality. We could plug in any number we want for x, and this statement will always work out. So far, we've been working with singular inequalities, but we also have what are called compound inequalities, which is just 2 or more inequalities put together. There's 2 different types. Our first type is called an AND inequality. When it comes to solving an AND inequality, we're just going to solve each inequality separately and then combine the answer. On our first one, we are going to add 1 to both sides. So 6 is greater than negative 2x. Then we need to divide both sides by a negative 2. And remember, when we are dividing by a negative, that is going to flip our inequality symbol. So now it's going to be less than. And we have -3 is less than x. Or we could also write this as x is greater than a -3. Remember, if we flip the order of the inequality, we also need to flip the inequality symbol. Now, when we solve our second inequality, 3x is less than or equal to 18, we're going to divide both sides by 3. So x is less than or equal to +6. This leaves us now with our two solutions. And we need to graph both of them. Starting off with x is greater than -3, we're going to have an open circle on -3, and we'd be shading everything that comes above. Then, with x is less than 6, we're going to have that closed circle, and we'd be shading everything below. But the solution isn't this. The solution is where the two overlap with each other. Therefore, our solution region is just between the -3 and the +6. That means we could plug in any number between -3 and +6, and it would make both inequalities be true. When it comes to solving an OR inequality, we're going to treat it the same way. We're going to solve each inequality separately, then graph the solution. On our first one, we again need to add 1 to both sides. So we're going to have -15 is greater than 5x, divide by 5, and -3 is greater than x. Or we could write this around as x is less than -3. With our second inequality, we need to subtract 9 to both sides. So 3x is less than -3. Divide both sides by 3. So x is going to be less than -1. Now let's graph our two solutions. Our first one, we're going to have an open circle on -3, and we are shading everything that comes below since it's less than. With our second solution, x is less than -1, we are having an open circle at -1, and we're also shading everything that comes beneath it. But since this is an OR inequality, we only need a solution that works in one equation or the other. So we have a much wider possibility of solutions. Therefore, we are going to include the shading from either inequality in our final answer. So our final shading would happen from -1 all the way to the left.